So last week we were introducing models for physical processes, chemical processes. Today, we will start, or we will finish the details for models for physical processes, and then we will switch. We will little by little start going into some more details on the core part of the class, that is the description of models employed to describe biological processes. So today we will deal with settling and resuspension processes, are still physical processes. Then we will introduce energetic factors. In particular, we will discuss solar radiation and the effect of temperature, or better, the way we model this very important driver, very important forcing, that is the temperature. And then we will start introducing a description about a nitrogen biogeochemical cycle. We'll finish with the biogeochemical cycles in 2 days, when we will introduce also phosphorus biogeochemical cycles. But today, now let's start by discussing settling and resuspension. These two processes, that are complementary processes, are very relevant from the point of view of ecosystem modeling, because we know that in the aquatic environment, the physical processes that determine the transport from the water column, for example, phytoplankton settling out from the eutrophotic zone and so on, to the benthic compartment, so to the sediment. The benthic means the bottom part of aquatic ecosystems, are key processes in order to understand how substances moves, and in particular how nutrient moves, as we will see. So the first process we will discuss today is settling, and then we will introduce a model for describing resuspension. Settling is the process that transfers substances from the suspended parts in the water column down to the sediment, the benthic part of the ecosystem. So here we are describing processes of movement from the hydrosphere to the lithosphere, and in particular, we are now looking at what happens to suspended solids in the water column, while these suspended solids are moving due to gravity, or due to gravitational attractions from the water column down to the sediment, to the bottom part of the aquatic ecosystem, that is the benthos. The basic hypothesis on which we build the settling model are that of non-interacting particles, so dilute solutions, means that we have suspended solids but are not too dense, so much more diluted, because in the case of very dense suspended solid conditions, then the processes are much more complicated and much more difficult to model. So we start by simplifying our life by making the hypothesis of non-interacting suspended solids particle, non-aggregated particles. This is not always true, of course, and in particular, this is not true when we are dealing with settling or sedimentation in wastewater treatment plants, for example. By now, as environmental engineers, you should be aware of the fact that, especially in wastewater treatment plant, sedimentation is a very important process that has to be controlled. How do we introduce the settling model? We start from the very basics of Newton's law. So we start by saying that the force, that is mass time acceleration of a particle, is equal to the resulting of forces acting on a particle. So we focus our attention on a particle. The particle is subject to vertical downward gravitational force. So this is gravity that is moving particles toward the bottom part of the water system, and then countering this vertical downward vertical gravitational force, we have two forces. That is the buoyancy forces, so Archimedes principle. So this describes the fact that particles in a water column may be buoyant, so are floating, and the other force is a frictional force. So we start by writing the first law of Newton. So the force mass time acceleration, or the force, is equal to the resulting vectorial resulting of applied forces. Then we start by explicitating these forces. In particular, the gravitational force depends on the density of a particle, rho p, times the volume of a particle times the gravitational acceleration g. The buoyancy, symmetrically, with buoyancy force is equal to the density of fluid times the volume of a particle again, times the gravitational force g. These two forces acting into the same direction. Of course, these are vectors. So here you have to also indicate in which direction the forces are working or are applied. And the third force, the frictional force, is equal to the drag coefficient CD multiplied by the area of a particle opposed to the motion of a particle. So this is the section of the particle in the direction of the movement of a particle times the density of a fluid times the square of the settling speed divided by 2. Of course, this is frictional processes in which we have a dependence of the frictional force on the square of the settling velocity. This is typical for frictional forces. You have dependency on the square of speeds. And the frictional forces depends also on the flow regime. So on how the water is flowing in terms of water speeds, and this is described by the drag coefficient CD. We start by assuming, as customary, that we are in steady state. So in steady state, what happens? That we have a regime settling velocity. So the acceleration is 0. So we assume a steady state, so that we can simply, by employing these three definitions and putting this equation to 0, we can simply obtain an expression for the settling velocity or settling speed v. So the settling velocity is equal to the square root of 2 times the gravitational acceleration multiplied by the difference between the density of particle and the density of a fluid multiplied by the volume of a particle. All these quantities are divided by the drag coefficient, the density of fluid, and A, in this case, A is this section of a particle opposed to the movement. In particular, if you have a spheric particle, A represents the area of the largest of the area of the sectional area of a particle in the vertical direction. So this is an indication of how the particles may oppose to movement. In the case of spherical particles, we may simplify this relationship by introducing the volume of a particle, of a spherical particle. You may recall that the volume of a spherical particle is given by 4/3 p, the cube of radius of the particle, which is volume, divided by the area opposed to the movement, p times the square of the radius of the particle. So this is the surface of the opposed to the movement, multiplied by the drag coefficient here, so that for spherical particle, we may write that the settling velocity is equal to 4g times the difference, so the square root of 4 times g, the gravitational acceleration, time the difference between the density of a particle and the density of fluid, multiplied by the diameter of a particle, divided by 3, drag coefficient, and the density of the fluid. Of course, with 4, 3, and density of fluid corresponds to 4/3 p times the cube of the root, which is the volume of a spheric particle. So for spherical particle, we simplify this relationship, expressing the settling velocity in this way. What is the drag coefficient CD? The drag coefficient CD describes the condition of the flow, so the condition of the water column, which conditions how water moves in the water column. For example, the drag coefficient, we know that depends on the Reynolds number. So the Reynolds number is exactly a coefficient describing the type of flow. The Reynolds number can go from 10 to a -4 to 1, that is for laminar flow. And then for turbulent flows, we have that the Reynolds number may go from 10 to millions, so very large numbers. In these cases, these are empirical relationships that link the Reynolds number but with the drag coefficient. So we may see that in condition of laminar flow, we will have a very large value of drag coefficient, while in condition of turbulent flow, the drag coefficient essentially is equal to 1. We may also recall that the Reynolds number describing the condition of the flow is also can also be expressed as the diameter of a particle times the density of fluid times the settling velocity divided by the mu, that is the viscosity of the fluid. So here we have a dependency of the Reynolds number on the density of the fluid and on the viscosity. Of course, these curves changes according to the shape of the particle. For example, the upper curve, this is valid for spheric particle, while for cylindric particle, we may employ with dashed lines. So it is slightly different. The common points are that while the Reynolds number grows, the drag coefficient decreases and goes to a constant value of 1, more or less around 1, in condition of turbulent flow. Some approximation on this definition. For example, if we consider laminar flow, so we are in the lowest part of the Reynolds number, so with drag coefficients up to thousands, tenths of thousands, then we may write that the drag coefficient is equal to 24 divided by the Reynolds number, and in this case, by substituting this quantity into the equation that we have just obtained by the application of Newton's law. So this equation, if we substitute the values of the drag coefficient as a function of Reynolds numbers, what we obtain for laminar flow and spheric particle is that the speed, settling velocity of the speed, so this is the speed at which the particles moves from the water column down toward the benthic part, is equal to the gravitational acceleration divided 18 times the viscosity of water multiplied by the density of the difference between the density of a particle and the density of the fluid multiplied by the square of the diameter of the spheric particle. This is the well-known Stokes law that you may recall you have derived in several other contexts. For sure, when you have studied wastewater treatment plants modeling, you have employed or you have derived the Stokes law for describing the fact that in these systems, there is a significant settling process that moves suspended solids from the water column down to the bottom. In the case of other shapes, like for example, in the case of algae that are slightly more complex shapes, we may introduce an equivalent radius or a correction factor that describes the dimension of the algae. In this case, we may have a slightly different expression for the settling velocity. In particular, we may say another extreme condition, turbulent flow. So we are in the rightmost part of the graphic. In this case, the drag coefficient in condition of turbulent flow is 1. And in the case of cylinders, we simply employ the surface area of a particle opposed to the motion. So in this case, the surface area projected onto the vertical line. In this case, we obtain for a settling velocity this approximation in which we have 1.82 times the square root of the difference of the density of particles and fluid multiplied by the diameter and the gravitational acceleration g divided by the density of fluids. This is a way of calculating by explicit application of Newton's law, that are the laws that describe the movement of a particle into a gravitational field. We may obtain these expressions for the speed, settling velocity. There are other ways for modeling this kind of processes. In particular, you may model the process of settling by simple empirical relationship in which you have no constant and in which you introduce a first-order kinetic dynamics. In this case, you may write that if m is the quantity of suspended matter, so with a density milligrams per liters, m, then you may write that the variation of the suspended matter is equal to minus s. S, it is the rate of removal by settling, but of course it is linked to the settling velocity v that we have just estimated divided by the depth of the system h, where h represents the mean system depth, so the depth of the water column. In this case, as you may imagine, this is a first order kinetic in which the solution is, as customary, the exponential, decreasing exponential. In this case, you may rewrite that the settling velocity expressed as the rate of removal of substances by settling, that is expressed as the ratio between the settling velocity v and the depth of the system, may be rewritten as a 1/3 the difference of the density of particles minus the density of water divided by the by mu, that is the viscosity coefficient. So here we have a dependence on the removal rate, on the density, difference of density of particles and water divided by mu, that is the viscosity. Of course, you know that the densities as well as the viscosity depends on temperature. So that if we look at empirical observation in order to evaluate the removal rate in terms of as a function of temperature and in terms of viscosity and density, you may recall from the lecture in which we described the specificities of water, that the density of water has a maximum value around 4 Celsius degrees, so this is the point in which we have a maximum density. And then when the temperature increases, the density tends to decreases. For the viscosity, we have the same process. So we have the same dependence, but the shape of the dependence is different. In the case of the density, we have a concavity that is toward the upper part, while in the case of the viscosity, we have a reverse concavity. The point is that if we look at this ratio, we want to understand where is the point of changing in terms of which of this quantity, density or viscosity, is dominating. So the point of inversion is here, in which we have the density that corresponds to viscosity, and after this point, density starts to decreases, while viscosity continues to increase, slightly increase. So that what happens, that up to this point, you will have that density dominates over viscosity, while when we pass this temperature, the situation is reversed, and we are in a situation in which viscosity tends to dominate over density. So it is not immediate to understand what is the effect of temperature on the settling, on the rate of removal by settling, but if we look, as customary engineers do, to this empirical abacus, in which, for example, you may describe the relationship between the sedimentation rate, so between the speed of settling, that is in meters per day, and the temperature, you will see that in general, as the temperature increases, the sedimentation rate increases as well. The increase changes in terms of the different densities of the particle. So, for example, for particles with higher density, you may employ this part of the graph, the higher part, but the overall effect of this is that in case of temperature increase, you will have an increase in settling velocity. So this means that I am expecting that as the temperature of the system increases, I will have less suspended matter in the water body because the settling velocity will increase, and as a consequence, the rate of removal of material by settling increases as well. Okay, this is more or less all you have, or you can use to describe settling. So you may start by explicitly employing Newton's law, and you can, by this, in the assumption of steady state conditions, you may obtain a relationship for the settling velocity, and you may find approximation of this relationship according to the condition of flow, so Reynolds number from laminar to turbulent flow, but also according to the different shapes of a particle. This is an explicit model, and it's very interesting because you have a lot of parameters that allows you to change your model according to the relevance of the different conditions, for example, densities or diameters of a particle, while here we have showed that in general, we may always employ a first order kinetics that describe the same process in an empirical way without giving much details about the microscopic processes influencing this settling process. The microscopic sub-processes that end up in a macroscopic settling effect. So two ways for modeling settling: explicit application of Newton's law, and you end up with the Stokes law formula, or empirical model, which depends from a couple of parameters, in particular the water system depth, and the settling velocity, that, as we have seen, depends essentially on the density, on the difference between the density of water and the density of particle, normalized by the viscosity of water. So this more or less ends up our description of settling model, and now it is time instead to give a look to the very important complementary process that is that of resuspension. What is resuspension? Resuspension is movement of material from the bottom part of the water system, or the water body, or the water ecosystem, toward the water column. So this is really the reverse process. During settling, you have movement from the water column, so the hydrosphere, toward the lithosphere in sediment in the bottom part of the ecosystem, of the water system, the water ecosystem, while in resuspension, you have a reverse process, that is movement of water from the lithosphere, the suspended solid, onto the dissolved water in the hydrosphere. What are the factors playing a significant role, especially in the process of resuspension? First of all, you have to include wind energy. And wind energy, how much energy is transferred from the wind onto the water body, depends on the speed of the wind. So this U is the speed of the wind blowing onto the surface of the water body, and the fetch. The fetch is a length or a distance over the surface of the water body that is exposed to the wind blowing. The larger the fetch, so the longer the distance, the higher will be the wind, the higher will be the waves generated by wind blowing on the surface of a water body. So we may understand this representation by, for example, describing what happens on the surface of a water body in terms of the distance from the border of the water body, so from where the wind starts to blow. So we may have a representation in which we have starting formation of waves. Waves are described by the wavelength L and by the height of the wave, that is hs. When you have this kind of waves, then by dissipative processes, you may have some kind of gyres that tend to distribute or to dissipate the energy of wind. Gyres start from larger gyres and progressing toward the bottom of the water body through smaller gyres until gyres reach the bottom of the water body. What happens when you have a water movement on the bottom of the water body? You have resuspension. So by shear stress, due to movement of the water, there is a force that we may indicate with tau that appears, and is a vertical force toward the upper of the water body. So this is really a force that is generated by shear stress and moves solids from the bottom of the water body toward upstairs into a water column. The waves, as we said, are described by the speed of waves, but is small v, by the age of the waves, but also by the period, or by the wavelength. The period is equal to a wavelength divided by the speed of waves. The energy in water is the energy of wind is transferred in water down to a depth h. In this case, we have a stress, a shear stress factor appearing due to the fact that the water moving on the bottom part, so moving exactly above the benthos or the benthic part of the water ecosystem, generate a force, a vertical upward force that we may call this shear stress. The ability of this force of taking away particles from the sediments, from the bottom of the water body toward the water column, depends on the sediment characteristics. So in particular, the sediment characteristics may be described by a quantity that is called critical shear stress, tau c, that depends on the sediment in terms of grain size distribution, and degree of consolidation. So the quantity of water that is present into the sediment itself. So the two factors of influencing resuspension are the two factors influencing resuspension that are characteristics of the sediments are the sediment grain size distribution. So larger grain sediments tend to resuspend with more difficulties. So we may say that gravel resuspend less than sand, for example, but also on the consolidation degree of the sediments, so that we may say that sand resuspends more easily than clay, for example, because sand is in general less consolidated than clay in terms of water content. How do we describe, or how do we formalize mathematically this model? We start by introducing a quantity, epsilon, the quantity of resuspended sediments. And we may say that the quantity of resuspended sediment is zero, will be zero, until the shear stress, so the stress generated by wind through the gyres that propagates from the water surface down to the water bottom. If the shear stress tau is smaller than the critical shear stress, then we will have no resuspension. So epsilon is equal to zero. On the contrary, if the shear stress tau is larger than the critical shear stress tau c, then we have an explicit model in which we may write that the quantity of resuspended materials is equal to some kind of constant. Yes? That is equal to some kind of constant multiplied by the difference between the shear stress and the critical shear stress elevated to a power of 3, to a cubic power. Epsilon is expressed in grams per cubic, in grams per square meters. So how many sediments, or how many grams of sediment is suspended per unit surface, while tau, the forces or shear stress, are expressed, for example, in the MCESy system in dyne per square centimeters. The values of the coefficients are, for example, 0.008 for the alpha coefficient and 10 to the cubic Newton over TD coefficient. In this case, we may also introduce some more details by assuming that we are going to model shallow water ecosystems. This means that we have an immediate transfer of the effect of winds on the surface of water body through the gyres and through the waves generated by blowing wind on the surface of a water body. For shallow water body, we may find an empirical relationships that give us an estimation of shear stress tau as 0.003 times the square of the water velocity u. U is the speed of water in centimeters per second at 15 centimeters from the bottom. And tau is a force expressed in dyne per square centimeters. Why 15 centimeters from the bottom? Because you may recall from your hydraulic classes that if you describe the velocity profile of water into a tube, you have as boundary conditions that the speed of the water immediately on the surface of the tube is 0. So that we have to build this model, we have to consider the velocities of water, the speed of water at 15 centimeters from the bottom. This is an assumption of a model for a suspension. In the case of shallow water bodies, also you may find an expression that links the speed, the water speed at 15 centimeters from the bottom with the condition, the effect of winds in terms of height of waves and period or length, wavelength of waves, multiplied by 100 divided by the hyperbolic sign of this quantity, that is the water body depth. So it is h, the depth of the water body, multiplied by the wavelength L, the length of the wave generated by wind. So concerning the suspension, what we may say is that the suspension depends on the wind flowing over the water system. It depends not only on the wind speed, but depends also on the fetch, so on the length that is available to the wind, so the length on which the wind can blow, and thus generating waves. Depends then on the fact that there is a shear stress effect due to water movement of 15 centimeters above the bottom. So we can calculate the shear stress, and depends also on the critical shear stress, that is a characteristic of the sediments. In this case, here you have a model that simulates wind but not currents. So here in this calculation of water speed at 15 centimeters from the bottom, we are only including the effect of wind that propagates from the surface of a water body toward the bottom of the water body through the gyres of water moving. And of course, the effect will become relevant only if we consider shallow water bodies or shallow waters. In particular, from again experimental observation, we may find relationships between, for example, the mean velocity at 15 centimeters. So this is this velocity u here. So the velocity that is generated by the gyres that are generated by the waves that are generated by the wind blowing on the water surface. So we may find empirical relationships that describe how is the effect of generating speeds at 15 centimeters above the bottom, and how this movement of water 15 centimeters above the water cause resuspension. And as we have said, this depends on the characteristics of the sediments, in particular on size or diameters of a particle, but may be expressed in microns, meters, microns. So if we make empirical observation on different conditions, for example, let's see how much sediment is moving from the bottom of the water system. This quantity of sediment depends on the speeds of the water at 15 centimeters. So how much the water is moving and generating this vertical shear stress force that moves material from the bottom towards the upper part. And according to the different condition of the sediment in terms of granulometry or size or diameters of the, and in terms of water content, or if you want, of consolidation degree of the system. So for example, we may say that for consolidated clay and silt, you will have immediate erosions for particles whose size are larger than 10 microns. While you will have erosions, means movement from the bottom toward the water column, else in this condition you will have transportation, that is horizontal movement of sediment particles. And for example, for lower speed limit, for lower 15 centimeters above the bottom speeds, you will have depositions. So you see on the vertical axis, you have the effect of winds that translates into the speeds above 15 centimeters, at 15 centimeters above the bottom, and the effect of winds that is counteracted by the characteristics of the sediment in terms of granulometry and in terms of water content. So you will have different curves according to different water contents. How can you employ these graphs? For example, let me see if I can make some drawings, terrible drawings. My terrible drawings, please forgive me. For example, we may say that if this is the size diameter of a sediment, sorry, oops. Okay, let's fix the size diameter at this point. Then you will have, according to the different mean water velocity at 15 centimeters above the bottom, you may have deposition, that is what happens for unconsolidated sediment, or you may have transportation, or you may have erosion, that is movement from the bottom toward the water body. Of course, in the case of high water content sediments, that is, for example, sand, you will have a much smaller quantity of material moved. Instead, if you have low water content sediments, let's see, these are percentages. So let's say 90% content of water, that is typical for the case of sands, while you will have 50% in the case of clay and silt. In the case of sands, in which you may have 90% water content, you will have a line, a curve, or a model like this one that identifies exactly the changing condition between deposition of sediments, transportation, and then resuspension or erosion, movement from the water body, movement from the sediment up to the water body, the water column. Okay, let's go on. Of course, are the characteristics of the sediments that determine if you will be in a deposition, transportation, or erosion condition, depending on the on the water speed of 15 centimeters from the bottom. Okay, this is a very complex model describing resuspension that you may employ if you want to describe the effect of winds blowing onto shallow water bodies. Remember, the assumption is winds that blows on along the fetch, so distance on the surface, and the effect of resuspension is linked to the depth, so that you will have larger resuspension to shallower water bodies. In deep water bodies, of course, you will not have important resuspension because the energy transferred from the wind to the water will quite quickly dissipate and disappear with depth. Okay, now let's go to some more details concerning energetic factors that are relevant for the description of physical processes. In particular, as we have seen, that is the energy coming from the sun that fires all the biological processes in the biosphere, we shall start to analyze the effect of solar radiation as the main energy source for ecosystems' primary production. Solar radiation is the forcing for many ecological processes, in particular photosynthesis, photolysis, but is also, as we have seen last week, the forcing for meteorological processes, but also from some heat transfer process like evapotranspiration and so on. So how do we include energetic factors linked to solar radiation? We may start by introducing a very well-known equation that links the energy of a photon to the frequency of a photon itself through Planck's constant H. So we may say that the energy of a photon is equal to Planck's constant H times the frequency of a photon, but by employing the dispersion relationships that links the frequency with the wavelength through the speed of light, c, we may obtain that the energy of photon is equal to H Planck constant times the speed of light divided by the photon wavelength. We have said that the Earth's surface dissipates energy by lowering the quality of energy. Photons are absorbed in the visible spectra and in the ultraviolet domain, and these photons, this energy is retransmitted in terms of heat or infrared radiation. I recall you, this is the graph by which we have started analyzing energy balances on the surface of our planet. So we said by 100% energy, this is the solar constant, with immediate reflection of some quantity of this energy, then this energy is absorbed by the various elements, first in the atmosphere and then indirectly or directly on the water, on the Earth's surface. This energy is totally given back by re-emission of the atmosphere. It is interesting to give a look how with solar constant energy, with energy arriving on the surface of the planet from the sun, we said that a measure the solar constant 1360 watts per square meter. So this is an energy flow because watts are joules per second. This energy is subdivided in terms of spectral bands. 9% is ultraviolet, whose wavelengths are those described here. And of these wavelengths, so down less than 0.34 micrometers, when you have that the 4% is absorbed and reflected in the stratosphere. The stratosphere is the upper part of our atmosphere, contrary to the troposphere, that is the lower part of our atmosphere. So this 9% is absorbed in these wavelengths. 41% of these 1360 watts per square meters are visible. So this is the quantity of radiation that it is responsible for photosynthesis process. Of this radiation, 46% reaches the Earth and is reflected after being used and degraded by ecosystem. So this is the 46%. Remember this figure, 46, because we will come often. This is exactly this 46 that is absorbed by the Earth, directly or indirectly, and that is employed for doing photosynthesis, because we have partially in the ultraviolet, but mainly in the visible part of the range of the wavelength. So this is this part of the radiation coming from sun that amounts to 46% is the radiation responsible of primary production. Then we have enough of this, we have of this solar radiation, that is infrared thermal radiation. And this is in the wavelength of infrared, that is from 0.71 micrometers down to 3 micrometers. Of this radiation, 50% is absorbed and reflected from the various gases in the atmosphere. And this happens into the troposphere, so in the lower part of the atmosphere. So we are talking here about greenhouse effects, and the gases are that absorb these energies. So thermal energy are CO2 or N2O or other greenhouse effect gases. So how do we model these energetic factors? First of all, so the energetic factors linked to solar radiation. First of all, we shall give an overview of the various currencies that may be employed for describing the energetic factors related to solar radiation. In this case, we may start by looking or comparing different currencies, in particular the base currencies is with watt per square meter, so the currency of the solar constant. Watt per square meters, here I have given a list of the various thermal energies, thermal currencies, sorry, the various energetical currencies you may employ. BTU is the British thermal unit per square feet per day. So you have a factor of conversion for watt per square meter. These are MKS. So these are MKS units. So joules per second per square meter, so this is a density of flow of energy, may be converted in BTUs or sometimes in Langlays, according to the type of model, to the currency of the model that you're going to employ, or they may be converted into kilocalories, or they might be converted in small calories. These are kilocalories per hours, or small calories per seconds. Again, these are energy densities. This is the well-known 4,182 Boltzmann. No, sorry, not equivalent of the work equivalent of a calorie, the Joule experiment, you may recall. And these are the same, but instead of being expressed per second, these are expressed per days, in which so simply you convert by multiplying the quantity here by the number of seconds per days, that is of 86,400 and something. Then we have a latter currency, that is the Einstein. The Einstein per square meters per second. An Einstein is a mole of photons. Of course, you cannot convert in a universal way from Einstein to the other currencies, because here we just count in terms of mole of photons. You may recall that a mole is 10 to the 20 elements and so on, numbers of photons. So the numbers of photons per square meters per second, so the Einsteins per square meter per second, of course, cannot be directly converted into the above units, because not all photons are equals, because photons are different in terms of their frequency. In particular, we are very interested in those photons that we may call photosynthetic active radiation, PAR, and we may say that 9 moles of photons in the visible range, so the photosynthetic active radiation, are necessary to fix 1 mole of oxygen into through a photosynthetic process, through a process of photosynthesis. So you may recall that photosynthesis means converting solar radiation into organic matter. You may employ the Einstein as a currency, because the Einstein is a useful way of measuring the number, the quantity of photons, and the quantity of photons that are necessary to generate 1 mole of oxygen by photosynthesis are 9 moles of photons in the visible range. 9 moles of photons in the visible range are necessary to fix 1 mole of oxygen. How can we model mathematically the effect of solar radiation onto the biosphere? We have to introduce some quantity, in particular the photoperiod. The photoperiod is a function of the day and of the latitude, and is the fraction of the day in which there is light onto your ecosystem. The photoperiod changes along the year, depending on n, that is the yearly angle, sorry, the n, that is the day of the year, expressed in integers, and a function of the latitude phi. So at different latitudes, as you know, we will have different photoperiods. For example, down in Cameroon, we are quite close to the equator, so you have quite stable photoperiodic condition, in which you have more or less 12 hours light and 12 hours dark during the 24 hours day period. The photoperiod may be expressed by astronomical models as a function of a day, of a year, and of a latitude. So where you are on the planet and when you are making this. So the photoperiod depends on the tangent of the latitude and on the tangent of the solar declination. The solar declination, of course, depends on the day of the year or on the yearly angle epsilon. The yearly angle describes which moment of the year we are, our planet is finding itself in its orbit around the sun. Then we have a practical astronomical model that describes the solar declination as a combination of sines and cosines, and sines and cosines as a function of the yearly angle. What is the solar declination? Is the angle between the line linking the Earth-Sun and the equator plane on the Earth. So it is exactly the solar declination tells us how much the Sun is high above the horizon. And of course, solar declination depends on the period of the year. So it depends on the distance of the planet from the Sun. The yearly angle instead may be made dependent on the integer number day, the integer number describing the day of a year, in which we make a difference between the assumption is to employ in terms of days, we employ the difference between the spring equinox, that is the 21st of March. So n equal to 0 will be the first day of March. N equal to 21 will be the spring the spring solstice. So it is the 21 of March, so that you have that the yearly angle will be 0 on the 21st of March. So during the solstice of spring, sorry, this is not the solstice, it is the equinox. Divided by 365. Then, if you look at what's happening in our planet in terms of latitude, you may give a look to this argument of the photoperiod function, that is a tangent of latitude multiplied the tangent of the solar declination. So you may have a maximum value of the argument of the tangent, sorry, a maximum value of the argument of the arccosine in the photoperiod function. The maximum value will be when you have the maximum latitude and when you have the maximum value of the solar declination. This quantity is always smaller than 1. The maximum value of the solar declination on our planet is 23.5 degrees. In this case, you may include or describe the interval for the photoperiod by observing that the maximum latitude on our planet will be 66.5 degrees, corresponding to, in this case, the Arctic circle, the Arctic polar circle. So above 66.5 degrees, we are in the polar regions. And then if you consider combination between the maximum value of the solar declination, that is 23.5, and the maximum value of a latitude that is 66.5, and you obtain that consistently with the definition of a cosine of the argument of a cosine or of the argument of arc cosine, then you will have a value that is smaller than 1. In particular, for higher latitude values, so for latitudes that are higher than the 66.5, it happens that our photoperiod function simplifies by becoming 1 or 0, being we in winter or in summer. In winter, the photoperiod in the Arctic area is 0, meaning that we have a totality of darkness all over the day in winter periods, while in summer periods, we have a reverse situation in which we have a photoperiod of 1, so you have daylight all over the 24 hours day. How do we obtain these relationships? Of course, these are obtained by astronomical models and astronomical observation. In particular, if we make some mean daily clear sky short wavelength solar radiation, so we measure in watt per square meters the solar radiation in the short wavelength area and in condition of clear sky, then we observe that the solar radiation depends on the latitude and day of the year, as we have just said. Depends on the latitudes, so going from the equator to the poles, and on the day of the year going from 1, that is March, and equal to 1, that is March, with 20, that is March, the 1st of March, and sorry, just 1 second, because I'm looking. Sorry, okay. I am back. Okay, if we make observation of solar radiation along the year, so from January to December, we discover that solar radiation, according to the different latitudes, going from 25, for example, that is tropical latitudes, down to 50, that is polar latitudes, near very northernmost latitudes, then you have this kind of curves. This kind of curves may be easily or may be very well modeled by simple model and by making a regression on real data and obtaining a function that gives us the intensity of solar radiation as a function of the day of the year. I recall you that n is equal to 0 the 1st of March, and n is equal to 21st on the spring equinox, and n goes to up to 55, 270, 232. That is the 365 days minus the days going to the 1st of March. Of course, this model depends on latitude and day of the year, but also depends also dramatically on the fraction of the covered sky. Covered by what? Covered by clouds. Because, of course, the clouds can limit the quantity of solar radiation that arrives onto the surface. How do we, so when we make this model, first of all, we assume that we are in a clear sky conditions. So the factor correcting for the presence of clouds will be equal to 0. In this case, by a regression on real data, you obtain a very simple sinusoidal model that links the quantity of energy arriving on the planet in terms of watt per square meter, so density of energy flow, with the day of the year. It's very important to notice that at different latitudes, you may have very different behaviors of a model for the incident energy on the surface of the planet. In particular, yeah, I made here a comparison between observed data. These are megajoules per square meters per day, so density of energy per day. So these are density of energy flows. In Venice, near my hometown, these are the data, so you can these are real data, so you can quite well approximate with data with a bell-shaped function. If, for example, we look at different latitudes, for example, Manila that is in the Philippines, and it is in a tropical area, we have a very different quantity of, very different distribution of incident solar light due to the fact that, for example, in tropical area, at tropical latitude, we are in tropical climatic conditions, so that there is the so-called rainy season in which you have a very low quantity of incident radiation from the sun due to the fact that in these cases, the sky is covered by clouds, so the C factor that we have neglected here, putting it to 0, C equals 0, is not anymore applicable for Manila. So this kind of model depends also on the latitude, not only on the latitude, but also on the area of the planet, depending on the climatic condition. So if you have an heterogeneous cloud cover over the year, you obtain Venice distribution. If you have a different cloud cover over the year, you shall or you need to employ a more sophisticated model. How can we take into account for the effect of covered sky into the solar radiation model? We start by simply making a balance of radiation in the surface, on the surface of the planet. We call Q in net incident radiation on the surface of the planet. Q in is equal to the quantity of radiation that is this is the quantity of net radiation on the surface is made up by the quantity of the short this is a short upper minus short radiation plus so these are quantities of radiations that takes into account the effect of clouds on the sky. In particular, here is the short wave absorbed by cloud minus the short wave reflected by cloud plus the long wave radiation absorbed by cloud minus the long wave radiation reflected by clouds minus the black body radiation that is a reference value. So you may make a solar radiation balance by writing that the radiation incident onto the surface is a function of radiation absorbed by clouds minus radiation reflected by clouds plus, sorry, in the short range, plus radiation absorbed by clouds in the long range, on the long wavelength range, minus the radiation reflected by clouds in the long wavelength region, minus the black body radiation. Then you may write that the net solar radiation, so net short wave solar radiation, so net subtracted by the cloud reflection is the QSC minus QSR, so this is the Q, the quantity of solar radiation absorbed by cloud in the short range, the short wavelength range, minus the quantity of radiation reflected by clouds in the short wavelength range. We have an empirical model, may employ an empirical model, but it may depend on the fraction of the covered sky by the square of the fraction of the covered sky. C is a fraction, so it goes from 0 to 1. You have 1 totally covered sky and 0 totally clear sky. For the long wave radiation absorbed by the cloud, instead you have this other model, long wave emission from atmosphere to the surface. Again, this may be made dependent on the fraction of the covered sky and on another parameter that is the dry bulb air temperature in Fahrenheit. And then the black body or the heat emission from water, that is the back radiation, that is the black body radiation, depending on the water temperature. So if you put all these models together, you end up with a description of the effect of clouds on the sky, on the covered sky, in terms of quantity of fraction, sorry, of the covered sky. For models with very short time scales, for example, a day, we may introduce, again here we are modeling the intensity of radiation, so the intensity of radiation arriving on surface. For short wavelength model, so short time scale model, for example, days, we may obtain these functions that tells us that the intensity of radiation at time t in hours, t is hours of a day, and that can vary from half of a photoperiod to a double of a photo, to minus half of a photoperiod to plus half of photoperiod. If the day length is normalized to 1, E is the radiation intensity and En is the mean daily radiation given from the model that we have seen here, given from this model. In this case, we obtain quite a detailed model that describes the intensity of solar radiation as a function of a day of a year through intensity N, that is the mean daily radiation, but depends on the yearly angle epsilon, normalized by the photoperiod. So normalized by the quantity by the fraction of a day in which we have light. And as we have seen, this photoperiod depends on the day of the year, so on the moment of the year, and on the place on which you are making your observation. So this is described by the latitude phi. Okay. Now I would like to finish this lecture. Give me 10 more minutes. I would like to finish this lecture by introducing nitrogen cycles. So, as we have said, biogeochemical cycles and in general, the idea of matter cycling is very important in order to, is very significant in order to model processes in ecosystem. In particular, this is very important for bioprocesses. So, biogeochemical cycles try to describe how chemical elements move within ecosystem. Biogeochemical cycles relevant for ecosystems are those of the elements that are essential for life. So we have around 30 elementary elements: nitrogen, phosphorus, silicates, carbon, iron, and so on. These are all elementary elements that are essential for life, so for the biological processes. We know that resources are not unlimited. So as we have said several times, recycling is essential for life processes. Cycling through the different media, land, water, air, and biosphere of the planet, so through the geosphere, is essential in order to understand or to define the condition, the ecological conditions of a system. I recall you that cycling of this element is all sustained by solar energy, that besides inducing climate, climatic condition, they also foster and govern all geochemical, biochemical processes. So it is all based on solar radiation. I recall you that the very general way for introducing geochemical cycles is that of observing that solar energy that is used by producers, primary producers, that use inorganic form of materials to produce organic form of materials. These organic form are used by consumers that produce, how would you say, that produce wastes in organic form. Wastes in organic form are treated by decomposers, so bacteria, that convert this organic form into inorganic forms, and are the inorganic forms that can cycle essentially through the different geospheres, from the atmosphere to lithosphere and to the hydrosphere. In particular, we are interested in cycles of gaseous elements like nitrogen, oxygen, or carbon. What is the relevant form of gaseous carbon? Of course, it is CO2. In these cases, atmosphere for the gaseous forms of elements may be seen as a storage or a reservoir and can play an important role in controlling the cycle of this element. For example, CO2, so carbon dioxide dilution, depends dramatically on the quantity of carbon dioxide we have in atmosphere. Atmosphere as a storage provides also some resiliency ability to the system. So this means that having this large reservoir for gaseous forms of elements improves the resilience or the stability of the system. One question, to what extent, is still open. This is true for nitrogen, oxygen, and carbon. For phosphorus, it is different, because in the case of phosphorus, the sedimentary cycles are very relevant. Remember that phosphates or phosphorus in general goes with the solid transport, so to the transport of solids. So in the case of sedimentary elements like phosphorus, land is the main storage, and to some extent it is less resilient than the atmosphere. Nitrogen cycle describe the balance of a diatomic gaseous nitrogen, that is, as I recall you, the 78% of the air volume, and only the 0.03% of the earth crust. Some interesting compounds of nitrogen, for you, of course, you know, ammonia, or the ammonium ion, or nitrate, nitrite, or various nitrogen oxides. Then our agricultural salts, like, for example, nitric acid, or nitric sodium, or calcium, cyanamide, and so on, are all elements, all compounds of nitrogen that are of utmost relevance for biological processes. Nitrate salts from nitrous acid, as I already told, are less relevant for ecological modeling, because in general nitrate very quickly oxidates to nitrate, as we will see soon. Why the nitrogen cycle is so important? I recall you that nitrogen is found in DNA, is the fundamental elements of vitamins, amino acids, proteins, chlorophyll. So it is a key molecule, but these are all key molecules for biogeochemical and ecological processes. Nitrogen is abundant in the atmosphere. So the gaseous cycles, remember, the atmosphere, 78% of the atmosphere is nitrogen. So it is a very important reservoir providing resiliency for the system. Nitrogen is very abundant in the atmosphere. As a consequence, nitrogen is often a limiting nutrient for primary production. Some compounds of nitrogen are toxic, and nitrogen is a key factor for controlling dystrophic processes like eutrophication process, that is a serious harm to coastal zone or to surface water bodies like lakes. So the nitrogen cycle is quite complex because of the several roles that nitrogen can play in biochemistry. So you may find nitrogen going from oxidation numbers from -3 in the case of ammonia to +5 in the case of nitrates. So you see that there are very large types of different oxidation states for nitrogen. The processes linked to nitrogen dynamics are essentially a reaeration, so oxygen that transfers from the atmosphere onto the water, so the dissolved inorganic water. Here we are dividing from inorganic materials, like for example CO2, oxygen, or inorganic parameters like for example the pH or the alkalinity, or into inorganic forms of nitrogen like nitrate, nitrite, and gaseous nitrogen. So this inorganic part is transferred to the dissolved water. So this comes from the atmosphere and goes into dissolution into the water column. And then these quantities of elements are employed by the biosphere's actors. Okay. From the various actors in the biosphere, the process are as always described in terms of arrows of exchanges. So these processes of transfer from the different quotas, from the different state variables, if you want, in our conceptualizations. So you have in the biotic biosphere, you have phytoplankton that feeds on various forms of nitrogen. Then you have upper layer organisms like periphyton, and these are what's called primary producers. So this is the primary production that converts through photosynthesis. So by employing solar energy, converts nitrogen into organic biomolecules, so bioorganic molecules. And then to the upper trophic level, for example, processes like predation, 15, grazing, transfer of nitrogen from primary producer to the upper, so zooplankton, fishes, and benthos to the upper trophic level. All these bioactors produce wastes, and the wastes generally are returned in forms of dissolved or in form of particulate to the detritus and to a sediment, and then from here are given back onto the water body. So you see, you can look at the various processes from different perspectives, and you can give different descriptions, or you can put the focus of your model onto different planes according to the objective of your study. Quickly, we go into the processes of transformation of nitrogen in water bodies. We are interested in water bodies because, as I already anticipated, water is a very important paradigm for all the biological processes. So atmospheric nitrogen, N2, is abundant but very inert. So before being used by living organisms, it must be fixed. So this is the biological fixation and process of transfer of gaseous nitrogen from the atmosphere into the biosphere. This process is called fixation, biological fixation, and is carried by bacteria like the blue-green algae. Blue-green algae is the largest families of bacteria, photosynthesizer bacteria, that you may find on the surface of the planet. The blue-green algae, besides doing photosynthesis, they are also able to fix, so to transfer nitrogen from the atmospheric water onto the biosphere. This is biological fixation. So abiotic nitrogen fixation may come also from lightnings at high temperature, industrial processes, and so on. In reality, the cycle becomes very complicated when we start looking at what happens between the aqueous condition and the solid condition. In particular, the bioprocess that transfers nitrogen in the form of ammonia or nitrates that are soluble from the water column onto the biosphere is called plant assimilation. Plants assimilate nitrogen in the form of nitrate or in the form of ammonia. From the water column, you have that nitrogen in the form of ammonia and in the form of nitrate are exchanged by the water column with the bottom sediments. This is a dynamical exchange, so this is settling and resuspension, the model that we have seen today. From up to down, this is settling. From bottom to up, this is resuspension. Nitrogen then enters the cycle flowing from primary producer to the trophic network of consumers. So here we are going up through the trophic chain. Then we have decomposition and ammonification, the process that the environmental engineers call mineralization. So this is the transformation of organic substances coming from excretion, waste of living organisms or dead organisms, and so on. So this transformation of organic substances by decomposition and ammonification. This is mineralization. So here you have mineralization when you transform organic forms of nitrogen, when you may find them dissolved in the water column, through ammonification. So you convert organic nitrogen into inorganic forms like ammonia. And then from ammonia, you go to the other inorganic forms that are nitrate and nitrate. Our important process, sedimentation and resuspension and burial. Sedimentation is settling, what we had just modeled today. Resuspension is a movement from the sediments to a water column. The epsilon model we have introduced also today. But in the sediments, you may have also the process of burial. This is movement of organic forms of nitrogen beneath, so maybe buried into the deeper part, bottommost part of a sediment. Then we have a very important process that is called denitrification, in which nitrates are transferred back into the atmosphere. This is done by denitrifier bacteria, and then the cycle is closed with nitrogen getting back to the atmosphere. Nitrogen can also go into atmosphere through volatilization. You have also seen, you may recall the Whitman model at the interface, transfer at the interface, with a model explaining the transfer from the hydrosphere to the atmosphere, volatilization. So ammonia volatilization is a process in which you have ammonia, gaseous ammonia in dissolved water. Gaseous ammonia dissolved in water is transformed into aqueous form of ammonium plus the ammonium ion, again in aqueous form. This process is also called stripping, and the environmental engineers know very well how to employ this process and to control this process in terms of temperature, pH, and availability of organic forms. Nitrogen mineralization, the so-called ammonification, in this case proteins and other forms of organic nitrogen are decomposed into ammonia. This is a bacteria-driven process in which you have bacteria that degrade nitrogen compounds and incorporate the produced ammonia we need. The excess is released as ammonium ions. Mineralization, nitrification, so it is oxidation of ammonia. I'm not spending too much time because I am sure you have already seen all these processes in the other classes. The biological processes that are relevant in the nitrogen cycle is nitrification. Nitrification is the conversion of ammonium nitrogen into nitrate and nitrate. This is also, you may call also this oxidation, ammonia oxidation. This is carried by two families of bacteria, the Nitrosomonas, that is responsible for the first step of conversion, and then by the Nitrobacter, that is responsible for the last step of the conversion, going from nitrate to nitrate to nitrate. Please note that the equilibrium constants of the two reactions, reaction 1, that of Nitrosomonas, and reaction 2, that of Nitrobacter, are very different. In particular, the second, K2, is much, much larger than K1. This means that the Nitrobacter work very fast in converting nitrate into nitrate. You may have heard me saying this already a couple of times. Please take into taking into account the fact that these processes are carried by bacteria whose ability or speed of processing is very different. In particular, the nitrobacter are much faster in converting nitrate into nitrate. The biological process of nitrogen cycle is dramatically dependent on temperature, on pH. In particular, there are optimum pH ranges for nitrification that are both expressed by these curves between 8 and 9 pH. There is a strong dependence also on the alkalinity. So we have two different dependencies for the oxidation processes. With dashed line is the first step, that carried by the nitrosomonas. First oxidation step of ammonia into nitrate, and then the continuous line refers to the second step that carried by the nitrobacter, but it is the last oxidation that converts nitrate into nitrate. Okay, nitrification is strongly influenced by temperature, so the maximum reaction rate depends on environmental conditions in which we are, so essentially on the temperature conditions. In particular, we have the optimal temperature between 10 to 22 Celsius degree. We have a fastest exponential growth, while between 30 to 35, we have a constant production. We have zero production in the 35 to 40 Celsius temperature interval, and we have no reaction at all above 50 Celsius degrees. These are models you may employ. Again, these are all Michaelis-Menten-like models. You may recall that we have a dependence of the concentration divided by concentration plus the semi-saturation factor. So if we make this as a kind of subsequent process, we may simply multiply with Michaelis-Menten model for the two sub-processes in order to describe the dynamic, for example, the variation in time of concentration of ammonia depending on the concentration of the presence of oxygen for the oxidation step of the transformation. So then denitrification, as anticipated, is the reduction process taking place in anoxic condition, so in which you may have a transfer, like a changement or a conversion of nitrate attacked as an electron acceptor and can be reduced to gas of nitrogen. So the only true way, efficient way of moving nitrogen from an ecosystem is denitrification. Again, denitrification is a process in which you have nitrate plus organic substance, and then you obtain water and CO2. So this is a kind of oxidation process in which there is a net CO2 production. This process is carried out by facultative bacteria. They can adapt their metabolism to use nitrates as electron acceptor depending on oxygen concentration. So in order for denitrification to take place, and I recall you that denitrification is the only true process for moving nitrogen from ecosystem, you have to guarantee that at least to some extent there are anoxic conditions, because denitrification is a process that can take place only into anoxic conditions. This is the basis of phytodepuration processes in wetland. You have oxygen that is transferred from the plant toward the roots, and from there, the oxygen allows the presence of oxygen allows oxidation processes like the conversion of inorganic nitrogen forms like ammonia into other inorganic nitrogen forms like nitrate and nitrate. This is oxidation. And then the oxygen that is transported from the leaves of the plant. I recall you that in the leaves of the plant you have photosynthesis, and photosynthesis produce oxygen. Then oxygen is transferred to the root zone, and in the root zone of plants in wetlands, you have a compresence of contrasting conditions in which you have low oxygen, so anoxic condition. So you have first oxic condition due to the fact that you have photosynthesis, and photosynthesis produces oxygen. When these oxic conditions are reflected in the concentration of oxygen in the root zone, in oxic condition, you have oxidation of organic matter, the two-step nitrification, the two-step for nitrification. Then even in the root area, you find in anoxic condition. And in case of anoxic condition, then you have denitrification processes that take place. So the nitrogen removal processes in wetland are nitrification in the rhizosphere by bacterial films oxidized in the sediment zone. So we are bottom here. We have again denitrification in the bottom. So in anoxic condition, we have conversion of oxidized forms of nitrogen like NO2 or NO3 into gaseous nitrogen. This requires anoxic conditions. Then you have another important process, that is the ammonia volatilization. But please remember that ammonia volatilization is a highly pH controlled process. So it takes place only for pH that are larger than 8, so in very basic conditions. And then another process for nitrogen removal is the plant uptake that takes away ammonium nitrates from the water body, from the water, and transfer them to the plant for production of organic matter. And then you have a barrier processes. So it is an interaction with sediments, so that moves nitrogen in the sediment. Okay, please take into account that nitrogen may also be transferred from the atmosphere to the other sphere by atmospheric deposition. Atmospheric deposition goes essentially with rain. And in order to conclude the lecture of today, we give a resume. What are the processes for nitrogen cycle? Nitrogen fixation. These are really the processes you shall be able to describe. Nitrogen fixation in which soil microorganisms in symbiosis with some plants. So these are bacteria or microorganisms present that are present in soil that live in a symbiotic way in an area that is around the root zone of plants. For example, legume may be able to fix atmospheric nitrogen and transform it into organic nitrogen. Then you have nitrogen accumulation by bacterial uptake, for example. These are heterotrophic soil organisms that convert ammonia to organic compounds like protein. So this is really nitrogen accumulation, or if you want, production of organic matter with which, as you know, probably is plenty of nitrogen. Then we have ammonification, that is the composition of proteins and other forms of organic nitrogen into ammonium nitrogen. Nitrification, that is oxidation. So it is oxidation of ammonia to nitrate. And then we have denitrification, that is a reduction of ammonia, nitrogen, sorry, of nitrate, oxidation of ammonia, nitrogen, and nitrate into nitrate, nitrosomonas and nitrobacter. When you have denitrification, so this is a reduction process taking place in an oxide condition in which nitrate acts as an electron acceptor, and it is then reduced to gaseous nitrogen. And then the last one is ammonia volatilization. It is a process taking place in solids or waters with high pH condition. We remember pH larger than 8. We are in basic conditions. Last things you have to take into account when you want to compute nitrogen biochemical cycles, you have to recognize that not all the forms of nitrogen are equally bioavailable. In particular, the organic forms that are maybe dissolved and particulate are bioavailable, and the inorganic form that may be ammonia, nitrate, and nitrate. These are inorganic forms but are bioavailable. What does this mean? This means that the organic forms, dissolved or particulate, are bioavailable due to primary producers, or are bioavailable to primary producers that convert elemental elements into organic matter, and then can start this conversion process also from the dissolved and particulate organic matter. While the inorganic forms like ammonia and nitrate are again bioavailable for the nitrobacter and nitrosomonas. Okay, I would stop here now because you are tired and I am tired. And we shall switch to some more examples of models by tomorrow afternoon, because the lecture of the